Yeah, I'm talking without a microphone. I just do that. Okay, next we have Craig Lee, who's going to be talking about spanning the scales, multi-platform approaches for integrated studies of biogeochemistry and physics. There will be a panel after the end of the session, so if you have questions that you wanted to ask Oscar, you can ask him then. Thank you.
Great. Thanks, Dave. So Oscar gave a wonderful overview of the different platforms and kind of the state of the technology. And I'd like to continue on the vein of what he was talking about and thinking about how we use these technologies and in particular how we address these challenges. You're going to see material from a bunch of different people here, some of whom are listed up here, and there's a whole bunch of material in here. But fundamentally, we're looking at a system where we have dynamics that go from the sub-mesoscale, which we heard a lot about a couple of days ago, right? So here we're talking about scales of hundreds of meters or kilometers, so very rapidly evolving dynamics that have impacts on both physics and biology. That's influenced by the mesoscale, scales of tens of kilometers, which strain these features out and really sharpen the gradients to create these kinds of dynamics. And then there's the global scale, which we'd like to be able to make larger estimates. So, but these things are all connected, right? The dynamics are often interrelated. So how do we kind of go from here to here, right? How do we start to connect those pieces with autonomous platforms? So it's a hard problem, right? We have physical dynamics. We've got biological and biogeochemical processes are all unfolding at a wide range of spatial and temporal scales. We have this demand for synoptic 4D sampling. Oscar said it, many people have said it during the course of this meeting. And we're always trading off between the sampling speed, the speed of our platforms, our ability to cover areas, and the time scales of dynamics. Right, so we're constantly working in this trade space. We'd like to be persistent. We'd like to be persistent because a lot of the processes we want to observe are episodic. They happen, they go away, and then they happen again at some other time, which we can't really predict. We'd like to be persistent because we would like to resolve the extended timescales. Seasonal timescales, we'd like to be able to resolve interannual timescales to start to get at climate variability, right? There are issues of climate that unfold at decadal timescales. How do we stay out there for long enough to actually test our ideas about how these things happen? In order to get this kind of representative spatial coverage, Oscar said it, we need scalable platforms, right? We need to be able to deploy things in large numbers. These things are critical. And importantly, the robots are getting to a point where they can allow us access to a lot of these spatial and temporal scales, which we haven't had access to before. I think this is an important point in that this is a new set of scales we can access that expand our ability to work from ships and work from moorings and the other things that we've been using. So it's not necessarily a replacement as it is an expansion of reach. So you've all seen diagrams like this before, right? We use them when we teach. But the point here is that we've got a lot of different processes that unfold at these range of scales, and they're all interrelated, right? They're all interconnected. It's often the interactions in the physical realm, the interactions between these scales we really care about, right, that we find fascinating. And we have a set of platforms that also have overlapping capabilities, and the real question is how do you form systems of these platforms to give you the kinds of ranges that you need within the practical constraints of our logistics, our ability to fund things, right, our available resources. We've got a lot of different platforms these days. Oscar showed a number of them here. Here are some others, right? This is kind of a rogues gallery of the different robots that we use today. They all have different characteristics in terms of speed, their ability to sample synoptically, endurance, the kinds of payloads they can carry, which are typically fairly limited for these platforms due to energy and size requirements, their depth range. And then they also have different characteristics in terms of the reliability, whether they're expendable, whether they're not, what kind of logistics they require, and these all factor into the cost and scalability of the platforms. So the real question is, what are the things good for, right? What can we use them for? And this is a really simple example taken from the physics. This is the California Underwater Glider Network. It's a boundary current array, if you will. This is the kind of region of a regional forecast model, nowcast forecast model. And the interesting point here is that you have an order of magnitude more glider profiles than you do Argo profiles over the same period of time. But look at the difference in distribution, right? You have floats that give you very wide coverage. This is the kind of coverage you need if you're going to make maps. Right? If you want to map things, you need that kind of broad coverage. You have gliders, which are giving you an order of magnitude more profiles, but in a very special way. Right? They're high-resolution profiles, very concentrated, very nice for looking at strong gradients, things like this, but they're not really the tool that allow you to make these broad maps. You take these two combined, and you allow yourself to connect the coast with the open ocean. You resolve strong boundary currents and these broad areas. So this is an interaction between these two capabilities, and it gives you a much broader capability in the region. The last point I'd like to make here is, this is sort of interesting. We think about gliders as being much more expensive than floats. They're different, certainly, but the per profile cost is roughly the same for these two platforms. Right, so we're seeing this sort of convergence in the cost of doing things, different capabilities for the different platforms. So I'd like to go through a couple examples. This is a pair of NASA experiments, SPIRS, looking at salinity processes in the upper ocean. One study in the Atlantic first, and then the Pacific second. You can see that's a very large number of people involved in these two things, a combination of more conventional platforms like moorings and autonomous platforms, robotic platforms. But really remarkable from the level of platform integration and the thinking about how you stitch these things together. One of the things that SPIRS did was it took a Lagrangian component and an Eulerian component. So a drifting component that was made up of profiling floats, surface drifters, and then mobile platforms that surveyed around those drifting elements. And then a Eulerian component centered around a surface mooring, which allowed you to penetrate the air-sea boundary and make flux measurements, with mobile vehicles surveying around the surface mooring. And you have different speeds of things, right? You've got gliders, which are about half a knot. You've got wave gliders, which are 4 times the speed, can go very quickly and do surveys. Very flexible logistics. This was kind of interesting. They used a schooner, a sailing schooner, to do servicing of the robots, which was a low-cost way of maintaining a presence out there. Turns out it's also an unpredictable way. The schooner's been broken down for a while, and so we've had trouble getting back out to surface platforms. But I think it's a good experiment. I think it's a good way of thinking about these things. This is a movie that Andrew Sherbina made, and what you're going to see is this set of platforms here. The wave gliders in green, the drifting float you see here, the regular buoyancy-driven gliders, this yellow thing, and then you've got a bunch of surface drifters. And you can see, a couple of knots you can actually keep up with the float. It's drifting pretty quickly. In this particular instance, the underwater glider is having more trouble keeping up with the float. It's running patterns with the float, but it's not necessarily running patterns around them. The schooner comes out and deploys drifters and does things like this over the course of this drift. But it gives you a sense for how all these platforms work together, the fact that the drift speeds slow down and they speed up as the float gets sucked into eddies and gets spit out again. We have other examples from experiments in the ice and from just float and glider experiments in the Arabian Sea where things are a little more controlled and we're using automated targeting. It actually is possible to run patterns around these things in certain environments, which is very interesting. But it's this interaction between platforms that becomes very valuable, right? It allows you to resolve this range of scales. So what does that allow us to do? Well, as physical oceanographers, we like to make maps, right? It's one of the things we do that's a step to making budgets, which is another one of our favorite things to do. And in this case, you're looking at maps of mixed layer temperature and salinity generated from a number of different platforms, moorings and these little diamonds, surface drifters and the triangles, gliders and the round circles, floats and the squares. And then the size of the dot gives you an idea of how close it is to the mapping time. The smaller the dot, the less relevant the data is. And these are all mapped with a base map from the remote sensing. So that's the background average, if you will. Decorrelation scales of 75 kilometers in 5 days, and I'll show you why those were chosen in a bit. But this gives you an idea of what you can do when you've got this range of platforms working. The wave gliders are actually capable of running various set patterns around this, and then the underwater gliders do slower patterns, lazier patterns in the area. We use those to start to make budgets. So now we can actually do an estimate of the tendency term, right, the time rate of change. We can estimate advection. We can estimate the surface flux terms because we have a surface mooring. The scales at which you estimate these things matter, right? The spatial scales over which you estimate the tendency term, over which you estimate the gradients and the velocities that you then use to estimate the horizontal advection terms. But done carefully here in these kinds of scales, 3-week averages, kind of 75 kilometer, 100 kilometer smoothing in the horizontal, we can get pretty good agreement between the tendency in the red and then the sum of all the others in the black, or if you look at the horizontal advection term in the green, which tends to be dominant for some of these things. It's not perfect, but it's a pretty good representation. But here's the thing. The scales over which you do these things matter. And what you see here is optical interpolation over 7 days, 150 kilometers, 30 kilometers, and 70 kilometers. So your eye picks up different sets of scales when you do this, right? When you try to estimate the tendency, the air-sea flux, well, the air-sea fluxes don't change, but the lateral advection term. So the red and the green terms change as you estimate the running mean. And what we're doing is we're assuming spatial scales and averaging over certain time scales. And one way to think about that is if you think about an effective time scale, right, is the velocity in this area changes. What does that mean in terms of the spatial scales that you really need to average over time, right? As things get larger, things get more smeared out, right? You have to average over a larger area if you want to make sense of these things. But as you do that, you start to lose the small scale processes. And you're really limited by the speed at which you sample things and the resolution which the spatial span and resolution over which you sample. And the trick is actually matching the spatial and temporal scales. So how does that translate to the biogeochemical realm? This is a slide that I've actually shown before here, but the idea that what we want to do is to be able to leverage very detailed measurements made on the ship to a set of slightly less detailed measurements that we can make from moorings or ice-based observatories, right, things that have fewer restrictions, onto the still more limited measurements we can make from mobile platforms where the power requirements and the size requirements are quite strict. And we do that by calibration and by developing proxies. And those are developed by matching in situ measurements to these more autonomous sensors. This was the North Atlantic Bloom experiment from 2008. I'm just going to use some data from that to illustrate the kinds of things that we can do. Again, this was gliders following a float, so we're working in a Lagrangian frame and trying to map the area around that float. We can do things like we can estimate POC from backscatter. Right? We develop proxies by looking at in situ measurements of POC and relating them back to two measurements, backscatter and beam C. And in cases where we can actually look at both of these things, say on a float, we have an indication of where the proxy is good and when it's diverging, and these two things start to tell different stories. This is Matthew Alkire's work, but if we can do net community production from nitrate and from oxygen, and we can do POC from backscatter and from beam C, then we can start to get at export, right? And he's done export. If you look at this, he's got estimates from two different oxygen measurements and from nitrate for NCP, and then two different estimates of POC, and then an export estimate from the difference. If we use those again and look at export rate and start to relate those back to the communities that we see at particular times. So here we're looking at export rate at two different points in the bloom cycle, two different communities when we're diatom dominated, when we're dominated by smaller cells, but we get very different export rates. And this is Ivana Setnick's work where we look at a community composition index. Because we're out there looking at the cells, we can start to develop an optical index for what communities are out there. In this case, it's chlorophyll over backscatter, fluorescence over backscatter. And we got very different signatures depending on whether we were dominated by larger cells or smaller cells. So in this particular place at this particular time, we use this as an indicator of who's out there. You put those two things together and you can actually map POC, you can map the communities, and when you put those two things together, you can start to make maps of export from the glider measurements. Right? So you've got these mobile platforms roving around, and they're measuring very specific optical properties, and you can use the proxies to start to make these larger maps. This is something that Melissa Omand has recently done, and it's kind of exciting because it's an attempt at looking at growth rates using Diel cycles of POC. She used a wire walker, which is a profiling instrument that drifts around and actually uses the wave motion at the surface to move this crawler up and down the line very rapidly. So she's measuring profiles of POC over depth in time, and that allows her to look at Diel cycles of POC. And if she assumes that there's overnight, there's no photosynthesis, just phytoplankton loss, and during the day it's both growth and loss, does linear fits to the nighttime losses, extrapolates, and then looks at the difference between these two things, she can start to estimate growth rates. And what she's done is she's estimated growth rates as a function of depth or as a function of PAR. In this case, she's plotted it and gets these fairly classic sort of photosynthesis radiance curves that start to look like curves that sit in the literature, right? So there's some hope that you can start to do these rates from these autonomous measurements in these sorts of conditions. So to finish up, I've got a couple minutes left. I just want to go over a couple large efforts that everybody's probably aware of. There's the Southern Ocean, SOCOM, Southern Ocean Carbon and Climate Observations Program. Large experiment trying to understand the role of carbon cycling, acidification, and nutrient cycling in the Antarctic. And interestingly, over seasonal to interannual timescales, so starting to stretch out over very long timescales. And what they're doing is basing this on the deployment of lots of BGC Argo floats, right? Roughly 80 floats, I believe, operational now in the Southern Ocean, profiling, combining that with Southern Ocean state estimates that are not just physical, but start to reach out into the biological and biogeochemical realm, and then feeding that to models. So this sort of full spectrum of work to extrapolate the observations into the larger scale measurements and start to understand large scale variability. That has really kind of bootstrapped the BGC Argo program. Right, so these are the BGC floats that were deployed as of March of this year, so earlier this year. You see most of the concentration is SOCOM, but the floats are starting to fill out in other areas, in more northern latitudes. And Ken and company have included this little table here, right, to kind of indicate a comparison of ship-based profiles over the past decade, or the decade span from 2000 to 2010, versus the number of bioargo profiles in 2016. It's a similar story with Argo, right? There's just been this dramatic uptick in the number of available profiles of the parameters that the floats were able to measure. So to conclude, probably went through that all way too quickly, but the point here is that, to reiterate, it's really multi-platform approaches that are going to give us the power, the observing power that we want, the ability to range over the scales, both temporally and spatially, that we really need to access. There's a real critical need to understand the matching between the spatial and temporal scales as we start to go into these calculations, right? It's very easy to start to use mismatched pieces when you start to put together budgets and start to make estimates. So it pays to think about the kind of scales of variability there and then the kinds of scales you can access with the platforms when making these calculations. We've been hammering on this idea of leveraging autonomous sensors through proxies for quite a while now, and I think there's great fruit in doing that. There are new sensors, right? So as we do that, the reach is going to just expand. The ability to scale up really doesn't just depend on the observations, but it depends on leveraging process knowledge, distributed observations, into state estimates and models, right? So it's that full spectrum, along with the remote sensing, that gives us the ability to scale to the globe, to global and kind of decadal kinds of timescales. We're not talking about getting rid of ship-based observations. Actually, we rely on them even more heavily. There's kind of no getting around the need for those measurements to develop the kind of understanding that we kind of rely on for the interpreting autonomous observations. And then finally, a few thoughts for the autonomy. The autonomous platforms really allow a new range of logistical approaches. So we can think very creatively about how we get the platforms out there and how we use them. They're sailboats, they're fishing boats, they're shooting things in from over the horizon. right? We can range over thousands of kilometers, so you don't really need to be close to your operations area to conduct the sampling. I'd like us to think more about what we consider to be expendable platforms. The key is to develop things that are low cost that we can scale up, we can deploy in huge numbers, right? But what do we mean by expendable? Can we get around being really attached to our hardware and think in terms of the data return? It just shows you a figure that shows you that, you know, per profile costs of gliders and floats are very similar. We don't think of gliders as being expendable. We do think of floats as being expendable. So how do we come around to this philosophy of platform use? That's what I have. Thank you.